Alright guys, welcome back to Underground Science, and in this video we'll be talking about electrons, energy levels, and quantum numbers. Alright, so pretty much whenever we used to draw Bohr models, right, in chem class or something, like you know how we got told the rule, like in the first energy level we can only fit 2 electrons, and then the second energy level we can fit 8, and then 18, and then 32, and so on. Well, why is it 2 and then 8, 18, 32, right? That's the most common for 4 energy levels. Why is it that we can only fit these specific amounts of electrons in each energy level? Well, we can actually figure that out by using quantum numbers. All right, so that's why we're going to look at electrons, energy levels, and quantum numbers, all right, to figure it all out. And we also got a little our handy periodic table right here. All right, so let's go ahead and get started right away. Okay, so when in our first energy level, just by looking at the periodic table, right, if you have to decide how many electrons can fit in the first energy level, well, we can see right here that there's only 1 and 2 elements here. So and these numbers right here on the side represent the energy levels. All right, so like for example, this would be our principal quantum number of n equals 1, and then this would be our principal quantum number of n equals 2. And by the way, if you need a refresher on what quantum numbers are, I got 2 videos for that for you guys, so make sure to go and check that out. I'll put a little card pop-ups during this video for that. Alright, but so this is n equals 2, and then this has a principal quantum number of 3, right? So the energy levels increase as you go down the periodic table. So if you have to see, okay, how many electrons can fit in the first energy level, right? Or if you go to the Bohr model, the first energy level is right here. This first energy level, how many electrons can fit? Well, you can just count the elements as one way, right? There's one element here, one element here. So you just know that, okay, there can only be 2 electrons in the first energy orbital, right? Or energy level, I should say. How many electrons can fit in the second energy level? Well, the second energy level is right here, right? This whole energy level right here. And if you count it up, we have 1, 2, 3, 4, 5, 6, 7, 8. So we can just tell right away, we can fit 8 electrons in the second energy level, right? Or the principal quantum number of 2. And then so on. You can keep on doing that. Let's do the third one. How many electrons can you fit in the third energy level? I don't know why I keep on saying energy orbital, but energy level, the third one right here in the Bohr model, you can see there's a lot, right? But how many? Well, you count it up, right? So the third energy level is right here. There's 1, 2, 3, 4, 5, 6, 7, 8. But we're not done, because probably our next video when we go over or a future video when we go over electron configurations, you'll see that what I just circled, right, these 8, 1, 2, and then 3, 4, 5, 6, 7, 8, that's part of the third energy level. And we can't forget our D-orbital, right, which is our, right here, these transition metals. We also have, or this whole row right here is also a part of the third energy level. All right, it's part of the D-orbital. All right, and we'll go more over that, or we'll go over that in a future video when we talk about electron configurations, but this also counts, and we have 10 here. So remember, we're at 8 for these, right? We had 1, 2, 3, 4, 5, 6, 7, 8, and then we have 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That's all part of the third energy level. So we can fit 18 electrons in the third energy level. And if you keep on going like that, how many can you fit in the fourth energy level, and so on? You're going to get, in this video, we're going to cover the most common pattern in the first 4 energy levels, which are 2, 8, 18, and 32. These are the amount of electrons you can fit in each energy level. All right, and we'll see how by using quantum numbers instead of looking at the periodic table. I mean, you'll have to look at the periodic table, but we'll work with quantum numbers also, which will help us decide how many electrons which will actually help us see why we can fit these specific amount of electrons in each orbital. All right, so let's go ahead and get started. All right, so before we start, let's quickly erase all of this, right, on the periodic table because we'll need this again. It's okay, we'll just write it again if we need to. So let's just erase all this. All right, let's scroll down for some space. Okay, so we said we can fit 2 electrons in the first energy level, right? So remember the first energy level is right here, okay, this whole row. Well, there's only helium and hydrogen here, so this is n equals 1, right? First energy level. And remember, if you watch the quantum number videos, we know that n equals 1. We're talking about n. We're talking about our principal quantum number. So when our principal quantum number n is equal to 1, we're talking about our first energy level. And then, remember, we find our angular momentum quantum number or azimuthal quantum number by subtracting n minus 1, right? So n minus 1 is 0 because 1 minus 1 is 0, all right? And remember, when our angular momentum quantum number is 0, we know we're working with an s orbital, all right? So let's write that down. So this tells us what? We're working with an s orbital. We're working with a s orbital, all right? And remember, now next we have to find our magnetic quantum number to see the number of subshells we have, okay? So to find our magnetic quantum number, you just do, well, let me write the symbol first. Remember, it's m sub l, and you go inclusive from your negative angular momentum quantum number all the way to your positive angular momentum quantum number. And in this case, we can see that if we were to do it like step by step, it would just be negative 0 to 0, right? So it's just 0. So we have an ml or a magnetic quantum number value of 0. And since we only have one distinct value here, this shows us that when in our first energy level and when we have an s orbital, because we're working with our first energy level, we only have one orientation, right, or one subshell of our s orbital orientation, all right, because we only have one value, right? We only have a 0. That's one distinct value. And so now that we know that, we only have one subshell, which is our s subshell, right, which looks like a sphere. So let me just draw that right here. Not a really good drawer, so I won't be drawing that much. All right, but that's our s subshell. Okay, it only has one orientation on a 3D graph, an XYZ plane. And each subshell, or each orientation subshell that we see, can hold 2 electrons. And because in our first energy level, because our angular momentum quantum number is 0, which means we only have one orientation, because we have an s orbital, and an s orbital is a sphere. So there can be only one orientation, only one subshell. There's only 2 electrons that can fit because we only have one subshell, and I just said that. Let me write that down. Each subshell, I'm just going to say each subshell slash orientation, right? Orientation can hold 2 electrons, all right? And because we only have one orientation, or one subshell, we should say, in our n equals 1 principal quantum number or energy level, we only see that we can only hold 2 electrons in our first energy level. All right, so let's go and write that down. 2 electrons is what we can hold in our first energy level, right? So that's why in our Bohr model we see this pattern 2, 8, 18, 32, right? Right here. Because in our first energy level, we just saw based on quantum numbers, we're working with a s orbital, and we only have one subshell for that because we only have one orientation. And each subshell can only hold 2 electrons, which is why we only have 2 electrons in the first energy orbital or energy level. All right, so that's pretty cool. Let's move on to the second energy level, which is going to be this right here, this whole row. Okay, and based on what we talked about before, we know that we're gonna have 8 electrons in our second energy level, right? A max amount of electrons of 8 in our second energy level, right, over here. So let's go and see why, or how we should say. So when our principal quantum number is 2, right, the same steps every time. So when our principal quantum number is 2, next step, what's our angular momentum quantum number, or our azimuthal quantum number? Our azimuthal quantum number is n minus 1. 2 minus 1 is 1. Remember, when we have an angular momentum quantum number of 1, we're working with a p-orbital. Alright? And so you're just like, okay, well, how many subshells are we working with? How many different orientations? Remember, we need the magnetic quantum number to figure out the number of subshells or orientations we have for our p-orbital. So when you do your magnetic quantum number, right, from inclusive negative angular momentum quantum number all the way, each number, to your positive value of your angular momentum quantum number. Okay, so when you do that, you're going to get -1. So we're going to write right here, -1, 0, plus 1. All right, because remember, it's negative L to positive L, and our L is 1. Here we see that we have 3 different distinct values, right? Because we have 3 numbers. And so that's what our magnetic quantum number tells us. 3 distinct values, which means we have 3 different subshell orientations of our p-orbital. So 3 different subshell orientations of our p-orbital. Alright, and I showed this in the last video, but let's show it again. Our 3 different x, y, z planes, right? One here, one there, and one here. And our 3 different p orientations are on each plane. So watch this, alright? So we're going to have one orientation like this. This is how a p-orbital looks, by the way. Alright, and we're going to have one orientation that looks like this. This is probably going to be the last time I'm drawing it because I suck at drawing. Alright, and then we're going to have one orientation that looks like this on the z-axis. Alright, and since we just named these orientations based on what axis it's on, so this one is our py subshell orientation, this is our pz oh no, not this one, this one's our pz subshell orientation, and this is our px subshell orientation. And why is it py? Because it's our p subshells on our y-axis. Alright, why is this a px subshell right here, or a px orientation? Because our our subshell is on our x-axis. And same exact thing for this one. Why is this our pz subshell orientation? Because our p subshell is on our z-axis. Alright, so we have 3 different orientations. And how do we figure that out? Based on our magnetic quantum number distinct values. Okay, and so because we have 3 different orientations here and 3 different subshell orientations, each subshell orientation, remember, right here we just said each subshell orientation can hold 2 electrons. So we have 2 electrons in our py subshell, we have 2 electrons in our px subshell, and 2 electrons in our pz subshell. That equates to 6 electrons so far, right? So now you're just like, okay, well, if we scroll back up in the Bohr model, we saw that we have 8 electrons in our second energy level. So why do we have 6 right now, right? Well, we can't forget about L equals 0. Okay, so that's the rule. As you go up in our energy levels and your angular momentum quantum numbers increase, you don't just have that specific angular momentum quantum number. All right, you have to, at the end, you have to include the previous angular momentum quantum number. All right, so we have 6 here, but then remember we had 2 here in our first energy level. Okay, so we have in total, and when we have our energy level equal to 2, our principal quantum number of 2, we have a py, px, and a pz subshell But we also we have to remember our S orbital, our S subshell. So you have to include that also, all right? Our S sub, I'll just say S, okay? So now you can see when in our second energy level, right here, we have 4 different orientation subshells, which is why it's going to be 2 electrons in each orbital subshell, right? In each subshell. So it's 2 electrons, 2 electrons, 2 electrons, and 2 electrons, which equates to 8 electrons. All right, so you can't forget your previous friends, right? Our L equals 0, you can't leave them out of the party. You have to include them also every time you increase. And we'll see that as we go on. Now we know why we have 8 electrons in our second energy level when we draw a Bohr model, right? That's why, because see right here, 1, 2, 3, 4, 5, 6, 7, 8. All right, so we're at 2. We figured out why it's 2 because of our angular momentum quantum number of 0. And then we figured out 8 right now because of our angular momentum quantum number of 1. But we just saw that only equated to 6 electrons total because we were just focusing on the 3 p subshell orientations, right? But then we corrected ourselves and we remembered to bring in our previous angular momentum quantum number value for electrons, right, which was 2. So it's not only 6, but you have to add the 2 also. Okay, so 6 plus 2, we said equated to 8 electrons, okay, because we also had to include our s orbital from the previous calculation. All right, so now let's go and look at n equals 3. So our third energy level, and see how many electrons can fit in there. Right? I mean, we already know we can fit 18 because I showed it to you above, but let's see how we figured out based on using our quantum numbers like we have been doing. Okay, so let's go to n equals 3. All right, let's scroll a little bit more. All right, there you go. N equals 3. All right. Again, same exact thing. We have a principal quantum number of 3. We're working with the third energy level, right? So next step, how do we find our angular momentum quantum number, or azimuthal quantum number? N minus 1, okay? So 3 minus 1 is 2. Sweet. Now we have to figure out what orbital we're working with. Well, when L equals 2, we know we're working with a D orbital, all right? So let's write that down, a D orbital. Next, we figure out the magnetic quantum number because now we have to know how many different subshells we're working with, how many different orientations, right? Because our main goal is to figure out how many electrons can fit in our given principal quantum number or our energy level. And to figure out the number of orientations or subshells, we use our friend, the magnetic quantum number, right? So the magnetic quantum number, again, is inclusive from our negative angular momentum quantum number all the way to our positive angular momentum quantum number. All right, and so it's 2, right? We can see right here our angular momentum quantum number is 2. So our magnetic quantum number range is going to be starting at -2, then -1. Remember, it's inclusive. You have to include all of it. 0, 1, and then +2. And for the sake of it, let's put a positive here too. All right. So how do I figure out the number of orientation or subshells we have? Well, count how many values you have in your magnetic quantum number, right? We have 1 distinct value, 2 distinct values, 3. Oh, I mean, I covered the 1. Shoot. 3 right here, 4, and 5. So we have 5 different orientations of our d orbital. All right, and I'm not even going to attempt to draw that because this was already as bad as it is, right? But we just know that, just get the concept down that in our P, we're talking about p orbital, we have 3 different orientations, right? 1, 2, 3. And our d orbital has 5 orientations, 1, 2, 3, 4, 5. Which means we have 5 different subshells, right? So how many electrons can fit in each subshell? Remember we said 2 electrons can. All right, so 2 electrons here, 2 electrons in this subshell, 2 electrons here, 2 electrons here, and 2 electrons here. That's 10 electrons. But didn't we say we can fit 18 electrons, right, in our third energy level, which is the most outer one right here? So so we're working with this one right now, n equals 3, and there's 18 electrons here. But then how do we only calculate 10? Again, we can't forget about our previous friends. We have to include L equals 1 and L equals 0. So even though our angular momentum quantum number is 2, at the end you have to remember that it's also L equals 0 and 1, and it's 2, what we're working on right now. So if you recall, when L was 0, when our angular momentum quantum number was 0, we just had one orientation, an S subshell, right? Which means we can only hold 2 electrons. So we have to remember to add those 2 electrons. And then, remember when our angular momentum quantum number was 1, we said we had our 3 different subshell orientations of our p-orbital, right? We had a py subshell, px subshell, and pz subshell. All right, and remember each subshell holds 2 electrons. So we have 3 p subshells, which is 3 times 2 is 6. So you have to add the 6 electrons from here. And then just now we said we're working with the d-orbital when we talk about our angular momentum quantum number of 2, which has 5 different orientations, and each orientation holds, or each subshell I should say, holds 2 electrons. And we just said that was 10 electrons. So we have 10 electrons when our angular momentum quantum number is 2, or whenever our principal quantum number is 3, or our energy level is 3, or our third energy level, right? And now if you add it up, 10 plus 6 plus 2 is 18, right? That's so cool, because now you can figure it out based on quantum numbers, actually figure out how and why we have 2 electrons in our first energy level, 8 in our second, and just now 18 in our third. All right, and let's do one more and see how many electrons we fit in our fourth energy level. All right, so again, the same process. We're talking about our fourth energy level, so let's write that down. N equals 4. All right, principal quantum number of 4. Sweet. What's our angular momentum quantum number, right? So our azimuthal quantum number is n minus 1. So that's 4 minus 1, which is 3. All right. When our angular momentum quantum number is 3, what orbital are we working with? We're working with our F-orbital. All right, so when our angular momentum quantum number is 3, or whenever our principal quantum number is 4, we're working with our F-orbital. All right, and actually I should say that your angular momentum quantum number is actually the quantum number that determines what orbital you're working with, okay? So make sure to calculate or look for your angular momentum quantum number to figure out which orbital you're working with. Next, we have to figure out the number of subshells we have, right? Because again, we're trying to figure out how many electrons can we hold in our fourth energy level. And again, we use our awesome friend, our magnetic quantum number, all right? Our magnetic quantum number, which is m sub L, is our inclusive range we have to include between our negative of our angular momentum, couldn't speak there, our negative of our angular momentum quantum number to our positive angular momentum quantum number. All right, if we go ahead and do that, you're going to get values of -3, -2, forgot the negative, -2, -1, 0, +1, +2, and +3. Now you wrote all that down and you're just like, okay, how do I know how many subshells I have? How many F subshells do I have? How many F orientations do I have? Again, the magnetic quantum number tells us that, right? You just laid it out. Just count the number of distinct values you just wrote. Okay, so 1, 2, 3, 4, 5, 6, 7. All right, that's 7 different values. That means we have 7 different subshells, 7 different F subshells, or 7 different orientations. So 7 F subshells. I'm also going to go say 7 different orientations for our F orbital. All right, and remember, each subshell can hold 2 electrons. So it's 2 electrons here, 2 electrons here. We keep on going, right? 2 electrons here, 2 electrons here, 2 electrons here. What's 7 times 2? 14 electrons. But do we stop there? No, because we have to remember our other angular momentum quantum numbers. All right, so let's go ahead and do that real quick. Okay, so go ahead and go to the next page so we have more room. All right, I just decided to erase the stuff above so we could focus on, well, we can just do it again, but real quick, because we already have 14 electrons. Remember, we need 32 because the pattern is 2, 8, 18, and 32, right? And this is our N equals 4. 32 electrons can fit in our fourth energy level. Okay, but we're figuring out how right now. So we figured out the 14 electrons, right? Where's the rest? But remember, we have to remember L equals 2 and L equals 1, all right? And L equals 0. So let's go and do that. So L equals 2, when L equals 2, we said what? We were working within a D orbital, right? D orbital. And since we already went over, I'm not going to write all of it down again, but since to save time, we're already 26 minutes into this almost. So L equals 2 is our D orbital, and then we said what? In our D orbital, we have what? 5 different orientations, 5 different subshells, 2 electrons in each subshell. So if we do the math, we're going to get 2 electrons times 5 different subshells or 5 different orientations, which is 10 electrons. All right, so now we have 10 plus our 14, right? So we have 10 plus our 14, so we're at 24 electrons now. And so far in our n equals 4, our principal quantum number 4, our fourth energy level. Now we have to focus on, we can't forget, remember, so L equals 1. We're just literally, from whatever you're doing, you have to remember each and every angular momentum quantum number before that. So I know we're at L equals 3, but we're also have to include L equals 2, L equals 1, and L equals 0. Okay, so let's go and do that. So L equals 1, we said we're working with a p orbital, right? And we said we had a px, py, pz. We had 3 different subshell orientations. Each subshell orientation can hold 2 electrons. So that's 2 electrons times 3 different subshell orientations. Sorry about that. Which is what? 6 electrons. Now we're at 30 electrons in our fourth energy level. And I bet you guys guessed it. Now we have to include L equals 0, which was our S-orbital, which is just a sphere, right? So it only has 1 orientation. Okay, and even if you didn't know that, if you don't know an S-orbital sphere and only has 1 orientation, remember, we can use our magnetic quantum number, negative L to positive L. Well, L is 0, so it's just one distinct value, which is just 0. So we have 1 orientation for S. And each subshell orientation, again, 2 electrons, and we only have 1 orientation, so 2 electrons more, and we finally reached our 32 electrons. And that's it. This is the amount of electrons our fourth energy level can hold. All right, so this is our n equals 4 capacity for electrons. And that's it, guys. That's how you figure it out using quantum numbers. So if we go and look at our periodic table on the previous page, which is right here, right, shows a better picture of the periodic table. And so if we look here, right, we have our s orbital right here. So this is our s orbital. And right here also, this helium counts as our s orbital too. So let's just make sure we save that. So all of these in blue is our s orbital. Okay, so s orbital. And then we have our d transition metals, our d orbital transition metals all over here in orange. So this is our d orbital. And then we have our p orbital all in black. All right. So these are our 3 orbitals, and then if you count for how many electrons can fit in the n equals 4, just by looking at the periodic table, you can do that by starting here. So 1, 2, then remember you can't start counting here because this isn't our n equals 4 orbital anymore. This is our n equals 3 orbital, right? It's our 3D orbital, and we'll talk more about that when we talk about electron configurations. All right. So 1, 2, okay, and then 3, 4. This is our 4D. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then back to our 4p orbital, 13, 14, 15, 16, 17, 18. Then we go to our 4f orbital, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, and 32. So we saw that we have 32 electrons also this way by counting on our periodic table. All right, but that's pretty much it. That's how you use quantum numbers to tell how many electrons can fit in each orbital or each energy level. And in my future videos, I'll talk more about cool topics in chemistry, about electron configurations, and other cool topics about bio and biochem and in physics. And I hope to see you guys there. Don't forget to hit that notification bell, and don't forget to like and subscribe. All right, guys? See you guys next time.